and learn from your mistakes. Okay? In general, when I've done this in the past, the exam averages that I've seen at this mark, about 60%, jump up to 78, 80%. Okay? So it does make a pretty marked improvement in overall exam scores. If you're happy with your exam score, by all means, you don't have to do this. Okay? But it will help your grade in the long run. I would highly recommend that everybody does it. You should be going back through and looking at your exams anyway. Okay? Yes? This is for everybody, regardless of what your score is. If you had a high score, realize that everybody else is going to potentially be doing it and could eclipse your score. Okay? So worst case, if you had a high score, you have less work to do as well. You only have to fix 1 or 2 questions, find out where that information is. So it's not going to be a big deal for those that already have high scores to go through and do the work. For those that have low scores, it'll be more work, but you didn't put in the more work on the front end of it to get the higher score. Okay, so I'm providing you that opportunity to get a higher score at the end. Okay? Questions about that? Okay, as far as homework goes, sapling learning is working. I think we're now up to 3 or 4 people that have started the first assignment. I'm still working on the Connect problems. I got through about half of the possible assignments or possible questions I could throw into Connect this morning. I should have that live as of this afternoon. Okay, so you should have access to that. The number of Connect problems is going to be a little bit different than sapling because at very least the very first question within sapling, first off, doesn't belong there. It should shift as far as sequencing much later in the homework assignment. Asks like 8 questions, okay, all in one little compact format, whereas Connect has divided those 8 questions up into individual questions. Okay? So you'll see a few more problems number-wise in the Connect assignment, but it's the same amount of problems that you would do in sapling. I am going through and matching them. The sequence may not be exactly the same, but the problems that you're seeing will be the same. Okay? And I'll try and match the sequence as best as I can, but I can't guarantee that. Okay? Questions about that? Yes?
When's it due?
I don't think I put a due date on that. Well, on sapling I did for sure, but I don't know what it was. And oh, then maybe I didn't put a due date on it. Because we're making the exam 1 extension due on Monday, I don't want you essentially being double worked on that. So I'll push the due date to Wednesday of next week, which means, again, you're going to have a lot of work building up. So I would highly recommend that you are working on it. You just don't have to stress about finishing it that instant. Okay. Saul, I think your hand first, but then we'll go to you. Oh, then Jay?
For the exam extension, when you go into Connect, how do you do the 3 attempts? It won't let you use it. Or will allow you?
So with Connect, I did open up practice for each of those. So it should be the exact same assignment. I just copied it and said practice. So you should have access to the practice problems indefinitely. Okay. Yeah, someone pointed that out before the exam, and so I went back and built the practice problems for that. I don't think we've got that issue with sapling, but I'll take a look at that to make sure. Other questions? Okay, good. We didn't waste too much time there. So, acids and bases, we've got textbook problems. It's kind of the sequence that we're going in as far as the textbook goes. What we spent a lot of time yesterday looking at were the definitions of our acids and bases, and in particular, we went through and we said, what's special about our Arrhenius definitions? Good phrasing? Yeah, pretty much sucks. Okay? So you don't have to worry about the Arrhenius definitions. Be more concerned with the Bronsted-Lowry. Okay? So when asked for definitions, those are going to be the important ones. Okay? If you have to move into organic chemistry, knowing your acid-base definitions is huge. So because I'm a fan of organic chemistry, I will test you on these definitions. Okay? So make sure you've got these 2 definitions, or the Bronsted-Lowry acid-base definitions nailed down. Okay? We looked at a couple things that we could kind of summarize. So given a structure, we could look for something to help us identify if it's an acid. What did we need to find? We needed a hydrogen in front, okay, of our formula. Okay. We'll push that, expand on that a little bit more, but as far as you're concerned with the problems that you'll see in the homework and the textbook and your exam, I will try my best to make sure that acidic hydrogen is put in front. If a hydrogen is buried within the structure, we'll assume that that hydrogen is not acidic, okay, for the sake of this class. What do we need to look for to identify bases? We wanted a source of electrons. And I did say that there were two places, though I didn't write it down. What were our two potential sources of electrons? Okay, a lone pair, so non-bonding pair, and you were right at looking at the Lewis structure. The Lewis structure would give you the lone pair. There's another big red flag that doesn't require the Lewis structure. Sure, I heard it. What's that? Hydroxide, yes, but that really only goes back to the Arrhenius definition. So there's something about an individual structure or formula that you would see that immediately triggers that's going to act as a base. What's that? Yeah, I heard it somewhere there. Negative charge. That negative charge may be kind of hidden from you. The way it would be hidden is instead of showing the actual negative charge, we put the counter ion on it. The counter ion would typically be a group 1 metal. So if you see sodium ion attached to pretty much anything, that anything carries a negative charge, and our sodium would be positive. Okay? So that negative charge is now a tip-off that we're looking at a base. Okay? Why does that mean it's a base? What was the definition of a base? A hydrogen ion acceptor or a proton acceptor. Okay? What charge is a hydrogen ion or a proton? Positive. To accept a positive charge, what charge do you need to be? Negative. Okay? So we're trying to apply those definitions back to the structural information and kind of pick up some approximative abilities. Okay? So we then looked at adding some extra definitions in here, our conjugate acids and bases. Decided that you guys were going to work on this on your own, and in theory you came up with that bottom part of this correctly. Any questions about how that bottom part was assigned? Okay. How did we know the bisulfite added or acted as a base? There's two ways you could know it. Okay, we could look for the negative charge, except this one's tricky because we look up here, also see the negative charge and it's acting as an acid. So we have to be careful with this particular kind of species. Okay, so that is a tip-off that it could be a base, but it also has the hydrogen in front. Okay, so we're running it both an acid and a base. How do we know in this equation it's acting as a base? We look at the overall reaction. So we'd be given the entire thing. And when we look at the product, we'd identify the piece that looks most like it. Which piece looks most like it? Left or right? Right? Yeah. The left one. What happened to go from the bisulfite to this species? It accepted an H+. Which definition matches accepting H+? A base. We now know that this species acted as a base. What if you weren't given the equation? What if you weren't given the products? How would you know it's acting as a base? It's a sneaky answer. If you weren't given the products, how would you know it's acting as a base? And you should treat it like one. Like I said, it's kind of sneaky. We could look to see what the other species is and decide if that's an acid. Okay? Unfortunately, water acts as both, so that doesn't work. Yeah, you need a little bit more information. I would tell you. This is now acting as a base. What does it form? Okay? So the only two ways that you can really predict this kind of a species, whether it's acting as an acid or a base, is if you're given the products so you can then see what changed and match that to a definition, or I tell you the definition. Okay? It is acting as a base. Do whatever you need to do as far as the reaction goes to make it act as a base, because I told you it's a base. Okay? So I told you so, and you've got products. Okay? Questions about that? I thought there was something else I was going to add in there. What was the idea of our conjugate? Where do our conjugates show up? We'll, by definition, always put our conjugate species in the product side. Okay? It's just kind of a definition as far as our terms. Our conjugate acids and bases are always on the product. Our acid and base are always in the reactant. Okay? We add that conjugate term just so that we can help determine where our species are. Okay? Any questions? Okay, they're saying no. So we can do a little bit of practice. Okay? What are each of these species? What's the first one? How do you know it's an acid? See the H in front, and it's hydrochloric acid. Okay? Sometimes you'll get easier questions where you already know the answer. That's fine. Accept it. Move on. So our first one's an acid. What's the next one? Base. How do you know it's a base? Okay, we've got all sorts of fun answers on this. We see that sodium ion. Okay, what was special about the sodium ion? Always dissociates, and we get Na plus and OH minus. We now have a negative charge. Negative charge meant base. What's the other thing, which I think I heard someone say? That we don't have an acceptor or donator necessarily at this point, because we can't see the reaction. We're only given this. OH, according to our Arrhenius definitions, was a base. Okay, so there's multiple ways we could identify that one. Sodium hydroxide, if we see hydroxide or that OH ion, we know it's a base. Okay? Next one. How do you know it's an acid? We see the H in the front. Okay, so that atom would be our acidic species. How about the next one? Okay, we've got base. Why do you call that one a base? Okay, I kind of accept the sodium. You can already get the idea that I'm getting repetitive with the sodium ion. We'd get C2H3O2 minus. We have that negative charge. What if I made it potassium acetate? Same thing. Okay, that's why I don't like you saying directly sodium. Okay, if you say group 1 metal, I'll accept that. Okay, because if I put in potassium, you no longer see that sodium ion, but potassium, as far as its chemistry, is same as sodium. It's one of those group 1 elements. We would expect it to be soluble. We do see this transition. Okay, last one. Group 1 metal, okay, I can accept that. Does that make it an acid or a base? This one's actually kind of tricky. So it makes it soluble. We get sodium ion and chloride. What did we say about sodium ion's reactivity? Nothing. Okay. Chloride, what do you see there? Negative charge, which would tend to make us think, okay, it could accept a hydrogen. So let's consider that. Let's say it accepts a hydrogen. It would act as what? A base. We got that negative charge. That sounds reasonable. What do we make? Hydrochloric acid. What's special about hydrochloric acid? I haven't quite hit this definition yet, but we'll hit it. What was it again? So I talked over you. Step further, not just an acid. What's special about hydrochloric? It's a strong acid. By definition, what do strong acids do? Dissociate into the ions. So if we take a look at this reaction, since we're comfortable now with equilibria, right? As soon as I form HCl, what happens? It dissociates into the ions. How much does it dissociate? Completely. That's our definition of strong, which means if it completely dissociates into the ions, does chloride ever pick up an H+? No, which means chloride can't act as a base. Okay? How do we know that? At this point, we're really going back to definitions. Okay? We'd have to look at that being a strong acid and kind of decide from there. Okay? We will evaluate some things that can kind of help you with that numerically, which is a bit unfortunate, but it's really going to be important to know the definition of HCl as a strong acid. And by definition, your strong acids completely dissociate, which means as soon as they form, they go right back to the ions. We have no HCl in an aqueous solution. If there's no HCl, can chloride ever react and form HCl? No. Okay? It's a bit odd on that one, but it ends up coming out that way. What does that mean as far as acid-base characteristics? It's neither an acid or a base. We typically call that neutral. Okay, for sodium chloride. Okay? Any questions about that? We will come back to our strong acids. Oh, oops. Was that conjugate pairs thing up there yet? I don't remember. Okay, what are conjugate partners, just in case? So we identify them as acids and bases. For HCl, what's our conjugate pair look like? Okay, so we could add it to water, and we would get H3O plus and, for those of you saying chlorine, careful, it's technically chloride. You don't get tested on your speech, so it's not that big of a deal. Which of these is the conjugate partner of HCl? Our chloride, okay, is the conjugate partner. HCl versus these two, which one does it look closest to? It's the chloride. Okay, we'll always rank it based on the not hydrogen part. Okay, so our conjugate base would be chloride. When we go through and look at the next one, oh, that one's really weird. We get sodium ion and hydroxide. And when that dissociates in water, let's put it this way, I won't ever ask you the conjugate partner for a base, or a strong base. Yeah, because I'm not quite sure what you'd slide on that one. If it reacted with water, be looking at H3O plus being its conjugate partner, okay, which is a bit odd. Okay, so I won't ask conjugate partners for sodium hydroxide or any hydroxide containing compound. Next one. What did we say that was, acid or base? Acid, which means we generate H plus or H3O plus and our acetate ion. What's our conjugate partner? The acetate, is that a conjugate acid or conjugate base? Base, it has that negative charge. So the conjugate partner of acetic acid is acetate, which is a base, okay, or a conjugate base. We move to the next one. Okay, this one gets a little bit trickier. All of your bases are tricky because you kind of have to add them to water and see what you get. So let me add that water in there so we can see it. Yeah. We go through and do our reaction. We'd get sodium ion, get hydroxide, and HC2H3O2 oh, not minus. Why is it not minus? Picked up that hydrogen in the course of the reaction. Okay. Which species looks most like our sodium acetate? It's a bit tricky. We get two pieces. We get sodium and the acetic acid. Okay, I like the pointing. We're looking at acetic acid being the conjugate partner. Why do we not look at the sodium ion? What does sodium ion do as far as solubility rules? Always dissolves. Okay, so your sodium ion pretty much disappears from all reactions. Typically, when I draw them out, you'll actually see me ignore those group 1 metals, and I'll stop drawing them. Okay, because as far as I'm concerned, they aren't going to do anything. So there's no reason to spend my effort to draw it out. Okay, so if we look at the conjugate partner, our conjugate partner, this guy out here, is that an acid or a base? Acid. So the conjugate of acetate is acetic acid. Okay, so we're trying to look for those largest pieces. When we move to the next one, do we have a conjugate partner in this? Conjugate acid or base partner? No, why not? It's neutral. We don't have an acid or a base to have conjugate partners of. Okay? So now the next part of this. This is my personal favorite, but nobody seems to like this. Okay, we're going to do a little bit of psychology 101. Okay? So we're going to pop up some pictures here. And, yeah. And you get to think of the first things that pop in your mind. What do we get? Probably thinking something along the lines of strong and weak. Okay? We classify the people that we see every day into individual categories. What does that mean about what we do when we look at chemicals? We get to do the exact same thing. Lucky you. So, let's take a look. I take a look at these individual reactions, and I would go through and say, you know what, that first one, yeah, that's definitely strong. I can see that. That stands out bright as day. That next one, that's a strong base. I can see that as well. Next one, yeah, it's not quite as strong. That's a little bit weak. Next one, yeah, I think that one's weak as well. Last one was neutral, so we don't have to worry about that. Everybody see why we got strongs and weaks.
What's the definition again then for a strong base? The same as an acid group?
It completely dissociates. Strong means it completely dissociates. Everybody knows how I came up with those being strong and weak. Okay. This is kind of intentional. I would guess most students would not know how to define these being strong versus weak. Okay. Some people are looking very, very carefully at the reactions and have triggered on one of the things that we could look at. Okay, what did you say, Mason? If we go through and look at each of these reactions, the first couple ones, let's see, let's do something like green, only go one direction, meaning we completely dissociate into those ions. What happens when we shift to the weak ones? They're in equilibrium, which means we go backwards and forwards, okay, back and forth between these two. If we're in an equilibrium system, by definition, we have the reverse reaction. It does not completely dissociate into the ions, and we end up with a weak acid or base. Okay? If it's not an acid or a base, there's no point in determining weak or strong on that. It's just neutral. Okay? So what we're looking for, trying to key in on, are those equilibrium arrows. That's one way to evaluate this. Okay? How else could we evaluate this? A couple other options. What would the equilibrium constant be for your first two reactions? How do you solve for the equilibrium constant? Products over reactants. What would you expect the size of your equilibrium constant to be for something that's a strong acid or base? It should be extremely massive because we have a huge product concentration. And our reactant concentration is actually so small that mathematically we lose interpretation of it. So let's just make it a ridiculously small number. Let's take 1 divided by infinity. Or sorry, that's the wrong way. 1 divided by 1 step above 0. Okay, what happens? You take 1 divided by 4 and compare it to 1 divided by 1. Which one's the bigger number? 1 divided by 1. The smaller the denominator gets, the bigger your overall answer gets. Okay? So when we look at our strong equilibria, our equilibrium constants are going to be massive. So how else could we determine if these are strong or weak? We look at the equilibrium constants. How do you know what the equilibrium constants are? Yeah, you could solve for it. That's one option. That's a bit painful. There's easier ways. On an exam, what would you think? I give it to you. You look at the equilibrium constant, you now know. Okay? On your homework, what would happen on the homework? This is one of the unfortunate things with this section of chapter. In theory, they would give it to you as well, except they're too lazy to go look it up. So what are you expected to do? You're expected to go look it up. Okay? So as far as the Connect and the Sapling homework, if you're asked a question to determine something that requires the equilibrium constant, you should be able to go look up the equilibrium constant in your textbook. Okay? Your textbook has massive tables of these. So you can look up that equilibrium constant and go ahead and use it that way. Realize on the exam, I'll give it to you. You don't have to do that extra step. Okay? What do we expect to happen with our equilibrium constants for our weak? So our strong, we said K was really, really big. Right? Much greater than 1. What about our weak equilibrium? Okay. We're probably looking at something closer to 1. In theory, or presumably in most cases with our weak acids, we're looking at a number less than 1. Okay. The closer it is to 1, the stronger the acid. Okay, because it's a bigger equilibrium constant. As soon as we clear 1, we're pushing into it being more like a strong acid. Okay? So we can use our understandings of those equilibrium constants to try and come up with these strong versus weak definitions. So it can be helpful to go ahead and use those. That said, you will be required to use those as well. Okay? So, some more definition things that we can tag on to this. Your strong acids will completely ionize in water, okay? Also known as strong electrolytes. Weak acids will ionize to varying extents. Okay, so we get weird equilibrium constants, either a little bit or under 1 or maybe a little bit higher than 1, but that's usually fairly rare. Okay? Your strong acids will always be really, really huge, massive equilibrium constants. Okay? So we could go back and look at those. There's another approach to figuring out whether it's strong versus weak. Okay, and this really only works for this class. How many strong acids are there? How many compounds do you think completely ionize into hydrogen ions and hydroxyl? Okay, not a whole lot. It's roughly 6 to 7. I forget how many I've told you to memorize, so we'll see that here in a second. So what you can do is memorize the strong acids. When we get into the weak acids or bases, there's going to be a whole lot more. So it's way too difficult to force you to memorize those. So what we'll do instead is have the strong acids and bases memorized. Okay? So as far as our strong acids go, some of those should look familiar. You see HCl showing up on there. So our hydrochloric acid showing up there. You see sulfuric acid on there. Okay? So have these structures memorized, okay, or these formulas memorized. When it comes to the exam, I will write out the name and the formula. Okay? So if you focus on the formula, you should be good. Mainly because I'm not sure I can name them all right now. Perchloric acid. Is that right? Cool. Sulfuric acid, hydroiodic acid, hydrobromic acid, hydrochloric acid, and nitric acid. So good, I did name them all. It's just the first one. Okay? So you should have those, I got to count, 6 acids memorized. I will expect you to have those memorized when it comes to the exam. Okay? When we move over to the bases, those get a little bit more difficult. Primarily when you look at a structure or a name for a base, you can almost always assume that it's going to be a weak base. Okay? The few exceptions are where we directly form hydroxide. Okay? So I gave a couple examples there, lithium hydroxide, calcium hydroxide. What we're looking at is group 1A and 2A cations bound to hydroxide. So if you see hydroxide, that's a pretty big tip-off that we're looking at a strong base. Okay, what does that mean for our weak acids and bases? What about hydrochloric acid? Is that strong or weak? It's weak. How do you know it's weak? It's not on the list. Okay? So what we would then go through and do is just assume that if it's not on our list, we're looking at our weak acids and bases. That way we don't have to know the equilibrium constants. We don't have to know anything about those particular structures. We've already got it narrowed down, and we can immediately jump across. Okay? Questions about that? Okay, so let's go ahead and take a look at some equilibria. So I want you to determine the concentration of hydronium ion, or a proton, hydrogen ion, and hydroxide ion in a 0.15 molar solution of nitric acid with an equilibrium constant of 240, and a 0.15 molar acetic acid solution that has an equilibrium constant of 1.8 times 10 to the minus 5. Okay? At this point, I am kind of expecting you to draw out all the ice chart stuff, so I'll leave out those steps, or leave up those steps. Try and go through and figure out what these concentrations would potentially be. I will give you a tip-off here. The hydroxide ion concentration is not going to be as easy to solve for because we haven't talked about how to solve for it yet. Okay, so don't stress about the hydroxide. The hydronium, you should absolutely be able to figure out. Okay? If you've got questions on where to go, raise your hand. I'll